So before we begin, we're going to derive a new equation. And to help us, we're going to start from an equation in the previous chapter. Remember that in order to relate Gibbs free energy at non-standard states to the standard state Gibbs free energy, we said this, that delta G, non-standard state, was equal to delta G at standard state plus RT times the natural log of the reaction quotient. Okay. Now, in this chapter, we've talked about this, that delta G is equal to negative N, the number of moles of electrons, times Faraday's constant times the cell potential. Okay, so what we're going to do is to rewrite this equation, the first equation that I'm putting in brackets, but I'm going to replace both delta G terms with negative NFE, okay, with the cell potential. So I'm going to write that negative N times F times E for the non-standard state, delta G, is equal to negative N times F times E, standard state, for the standard state delta G, plus RT, natural log of Q. All right. Now, it is, I mean, if we can we cancel out things? We sure can. Okay. So one thing that we can, we can try to simplify this. Now, for convenience, it is generally, but not always, written as this, that the cell potential is going to be equal to the cell potential at standard state minus 0.0592 volts divided by N, the number of moles of electrons, times the log of Q. All right, so sometimes that equation that we have on the top over here, that I just drew an arrow to, sometimes this is written as a shorthand. Okay, and I'm going to put this in brackets. Now, this is only valid, though, if we're at standard state temperature. So the temperature has to be 25 degrees Celsius, 298 Kelvin. Okay, so it's got to be at standard state. And this equation that we're talking about right here is called the Nernst equation. So this is our way of relating Gibbs free energy and cell potentials we're relating it to the equilibrium in some way, shape, or form. Right now it's reaction quotient. Okay, so let's try a problem out. So here it is. Consider a galvanic cell that uses this following equation. Copper solid plus 2 moles of Fe3 plus yields 2 Fe2 plus. Copper 2 plus 2 moles of Fe2 plus. Okay. What is the potential of a cell at 25 degrees Celsius that has the following ion concentrations? And then the concentration of Fe3 plus is at 1.0 times 10 to the minus 4th molar. Copper 2 plus is 0.25 molar, and then concentration of Fe2 plus is 0.2 molar. All right, so we've got a lot of stuff going on here. So first thing we need to do is figure out, and I'm going to make a laundry list here of things that we got to do. First thing that we're going to need is the cell potential at standard state of the system. All right, in order to use the Nernst equation, we got to get that. Okay. Number 2, once we get that information, once we get the cell potential, we need to find Q. Now, what's really nice is that we do have the concentrations, so we can pop those in, get Q, we're good. Once we get those two pieces, the third part is to find E, and that's going to be using the Nernst equation. All right. So that's kind of our plan for this problem. Okay, so let's go back to the standard reduction potentials and find out the voltages of our half cells. So we're going to have one half reaction that's going to be copper going to copper 2 plus. Okay, and then the other half reaction is going to be Fe3 plus going to Fe2 plus. Okay, so if we go back to the cell potentials, so let's go back to that point in the notes. All right, so here is, I'm going to do this in a different highlighting color. So let me use pink here. Here is the iron. Okay, Fe3 plus electron gives us Fe2 plus. And then we got a voltage. All right. And then we've got to look for copper. So copper 2 plus 2 electrons right here. And there's our voltage. Okay, so what I'm going to do is let's go back to the problem, and I'm just going to write the two equations as is, and then we're going to deal with whatever we got to deal with. Okay, so going back to our problem, let's write those two half reactions as we had it. So for the first part, where we're calculating the cell potential, one reaction was this. Fe3 plus, which is aqueous, plus an electron, yields Fe2 plus. And the voltage was 0.77 volts. Okay, the other reaction was copper 2 plus, okay, plus 2 electrons yields copper solid. All right, and then that voltage was negative 0.34 volts. All right, so question. Well, it's not really a question. Let me take that back. All right, so look, keep in mind, you got 2 voltage. You got 2 moles of electrons. You got 1 mole in the first half reaction. So we've got to double the first equation. So that way the number of electrons are matching. Okay, but when we double that equation, we leave the cell potential alone. So we're good. But here's the next question. These are written as reduction half reactions. One of these is oxidation. Which one is it? Well, to answer that question, we got to go back to the original equation. Copper is solid and it's elemental, so it's got an oxidation number of 0. Becomes copper 2 plus, so it's got to lose 2 electrons. So copper is the half reaction that we're going to flip around. So I'm going to draw the flip. So that tells us that that's the reaction that we got to flip around. So let's rewrite what we've got for the two reactions. So let's double the first half reaction. So 2 Fe3 plus is aqueous plus 2 electrons yields 2 Fe2 plus. And the voltage is 0.77 volts. And then the second reaction, half reaction, solid copper goes to copper 2 plus 2 electrons. And then that voltage is going to be, that voltage should be negative 0.34. And I just noticed from my notes that when I brought this equation over, I already made it negative. In the table, it's a positive. So if you're wondering what's going on, that's I kind of goofed. Sorry about that. So now that we've got the 2 electrons, we can cancel those out. We can add up the two equations, half reactions, so that way we get our full equations. So 2 moles of Fe3 plus solid copper yields copper 2 plus 2 moles of iron 2 plus. If we add up the voltage, a negative 0.77 plus a negative 0.34, that should give us the cell potential for this reaction should be a positive 0.43 volts. So this is going to be definitely a positive value. All right. So now that we got the cell potential, the next part is that we need to calculate the reaction quotient, Q. And so if we are going to write the reaction quotient, that's going to be based on the concentration of copper 2 plus times the concentration of Fe2 plus squared divided by the concentration of Fe3 plus squared. Okay, so let me rewrite that Q. Okay, so Q is going to be the concentration of copper 2 plus times the concentration of Fe2 plus squared. So the concentrations of the products divided by the concentration of the reactants, Fe3 plus concentration of Fe3 plus also squared. Now, keep in mind, Copper is solid because it's not aqueous. The concentration of copper does not change, so we do not incorporate that. We do not include that into our reaction quotient. So according to our problem, we know those values. Concentration of copper 2 plus is 0.25 molar. The concentration of iron 2 plus is 0.20 molar, and that number is going to be squared, divided by the concentration of Fe3 plus, and it's going to be 1.0 times 10 to the minus 4th molar, and that also will be squared. Okay, so if you take 0.25 times 0.2 squared, and then divide it by 1.0 times 10 to the minus 4th, that value also squared. That value should be 1.0 times 10 to the minus 6th. All right, so we got our Q value, we got the cell potential, so now we can use the Nernst equation. So that's our step 3. The Nernst equation. So let's do it. So the Nernst equation says this, that the cell potential, okay, is going to be equal to the standard cell potential minus 0.0592 volts divided by N times the log of Q. Now, the only thing that we don't have, we've got Q, we've got the standard cell potential, we just don't know N. But we actually do, because if we go back to N is going to be the number of electrons that we've got. And we cross that out, but that was 2. So N is going to be 2, because we're getting it right from our half reactions. All right, so popping in our values. The value for the cell potential at standard state was 0.43 volts minus 0.0592 volts divided by 2, because that was the number of moles of electrons, times the log of our concentration, which is 1.0 times 10 to the I'm sorry, that was not that's not a negative, that's a plus 6. All right, plus 6. Okay. So that will be, if we figure out the right-hand side of the equation first, 0.0592 divided by 2 times the log of 1.0 times 10 to the positive 6, that's going to give you 0.18 volts. So if we take 0.43 volts minus 0.18 volts, the cell potential should be 0.25 volts for this reaction. And there you go. So now, because that the cell potential is a function of concentration, we can use measurements of the cell potential to determine concentration. So that's pretty cool. So we could go the opposite way and figure out concentrations if we need to. Now, there is something really cool about using the Nernst equation. So, and I had mentioned just a moment ago that the electromotive force E is going to be a function of concentration, and so we can use measurements of the cell potential to help us determine concentration. So what I want to do is use that. Let's use that to our benefit for a second. So electromotive force is going to be a function of 3 things: temperature, it's going to be a function of concentration, and it's also going to be a function on species, more specifically oxidation states. Okay, so what we're going to do is eventually use this to calculate pH. So let's do this. So let's give the standard reduction potential and related chemical equation for the standard hydrogen electrode. So this is going to be 2 moles of hydrogen ions, which is aqueous, plus 2 moles of electrons yields hydrogen gas. Okay, and the electromotive force for the cell potential is 0. Now, in the previous chapters, what did we use as a convenient means to measure the concentration of hydrogen ion? We use pH. And so we can see that measuring EMF can be used to measure pH as well. Now, the details are not really important right now, but that being said, if you go forward and go into analytical chemistry, usually that's like the next stepping stone right after doing Gen Chem. This is something you'll definitely focus in on. But the concept is really powerful. Now, EMFs can be measured accurately and quickly, and we can measure the EMF of a pair of electrodes dipped into a solution and measure not only the pH, but it can also determine the concentration of other ions. And this is really useful, like in water analysis. And these are called specific ion electrodes. Okay. Now, a couple of things to talk about. Calibrating these electrodes must be done carefully, especially for low concentrations. So it's super, super powerful, but you've got to know what you're doing with calibrating the electrodes. If you don't, your calculations are going to be way, way off. Okay. Now, of course, everything is temperature dependent. And, we got to see the Nernst equation for that because you've got a temperature factor in there as well. All right, so here is our problem. What is the pH of a solution in the anode compartment of the following cell if the measured cell potential at 25 degrees Celsius is 0.28 volts? Okay, so what I'm telling you is that 0.28 volts, that's your E cell. Okay? Now we need, and I give you the cell notation. All right, so you got platinum, and then you got hydrogen, and then you got a concentration of H plus ions, and that's in one side. That's your anode. You've got lead 2 plus, and then you got solid lead. Okay, and that's your cathode side. All right, and the concentration of lead 2 plus is 1 molar. You got solid lead, so that's not going to factor into the equilibrium. So what we want to do is use the Nernst equation. Okay, so let me write the Nernst equation down. And it says this. The E is going to be equal to the cell potential at standard state minus 0.0592 volts divided by N, and that's equal to the log of Q. Now, once we know log of Q, that's what we're going to use to help us determine pH. And we got a couple more steps to get there, but that's what we're going to be solving for in this problem. All right, so we got to know the number of moles of electrons, but we also have to know the cell potential. To get the cell potential, we've got to use the cell notation, figure out our half reactions, go look them up in the standard cell potential chart table, and then figure out what is the standard cell potential at standard state. Once we have that, we could solve for Q because we've got E because that's given to us. Once we solve for Q, we're home free. So that's our plan of attack for this problem. All right, so let's take a look at the half reactions for this. So if we take a look at the anode side, you've got platinum, which remember that's non-reactive. So we're going to ignore platinum for a moment, but you've got hydrogen and H+. You do have this half reaction, which H2 gas yields 2 moles of H plus ions and 2 moles of electrons. And the cell voltage is going to be 0. That's your standard hydrogen electrode. So the standard voltage is 0. The other side is that you got Pb2 plus forming lead solid. Okay, and then that's going to take up 2 electrons. So the electrons are going to be on the left hand side, and the voltage for that reaction is going to be negative 0.13 volts. So if you add these two together, the electrons drop out, but remember that this is going to be your N value right here. All right, so you got H2 gas plus Pb2 plus ion yields 2 hydrogen ions plus lead solid. Okay, and that is going to give you the cell potential at standard state should be negative 0.13 volts. All right, so what we're going to do is pop this into the Nernst equation. Okay, so here's what we got so far. We know that, remember the problem is 0.28 volts. That's your cell at non-standard state. So 0.28 volts is equal to negative 0.13 volts minus 0.0592 volts divided by the number of moles of electrons, in this case 2, times the log of the reaction quotient. So we're going to solve for that reaction quotient. Okay. All right, so we've got to get the log Q by itself. So first thing we do is add both sides. Add to both sides 0.13 volts. So this becomes 0.41 volts is equal to negative 0.0592 volts divided by 2 times log of Q. If we multiply, we got to get rid of the denominator. If we multiply both sides by 2, we should have 0.82 volts on the left. And that's equal to negative 0.0592 volts times log of Q. And I'm going to put the log of Q in parentheses so that way we don't get it confused. So now we got to divide both sides by negative 0.0592. So we get that the log of Q is going to be equal to 0.82 volts divided by negative 0.0592 volts. And so that log of Q should be negative 13.85. All right, so now if we try to take Q, if we take if we undo the logarithm to get Q by itself, 10 to the log Q is going to get us Q by itself. So basically what we're going to do is 10 raised to the negative 13.85 gets us Q. And so that's going to give us a value of 1.41 times 10 to the minus 14th. Now, we've got to figure out what this Q actually means. So, going back to our problem, if we were to write, if we were to write an equilibrium expression or a reaction quotient expression, that would be the concentration of H plus squared divided by the concentration of Pb2 plus. Okay, H2 doesn't matter because it's a gas. Pb is a solid, so that's not, the concentration is not going to change, and there you are. Now, going back to the cell potential, you're told that the concentration of Pb2 plus ion is 1. So if that's the case, if we replace this with 1, whatever the concentration of H plus is, squared divided by 1 is just going to be the concentration of H plus squared. So Q is going to be equal to the concentration of H plus squared. And so that's going to be equal to 1.41 times 10 to the minus 14th. And so if you take the square root of both sides, you're left with that the concentration of H plus is equal to 1.19 times 10 to the minus 7th. Now, if you remember, pH is found by taking the negative log of the concentration of H plus ions. That if we take the negative log of the concentration of H plus, the pH is 6.93. And so that's pretty cool. That's how a pH meter works. That's exactly how it is. It's measuring the cell potentials. It knows what its standard state is. And so it's going off of that. That's pretty cool.